Assalamualaikum warahmatullahi wabarakatuh. My name is Diah Tiyas. I'm from IPB University Indonesia. Now I want to give a talk about our recent result on understanding Kelvin wave activity in UTLS over the maritime continent from GPSRO measurement. This work is in collaboration with Dr. Sandro Lubis MSc from Rice University, United States of America, and Sonni Setiawan MSc from IPB University Indonesia. And in this first section is the background of our topic Kelvin wave. Kelvin wave are one of the various disturbance that form in a tropic region and propagate in the zonal direction. Kelvin wave influence the dynamic of the atmosphere. In the several previous studies have shown that Kelvin wave affect rainfall significantly in a tropic with a contribution 16 to 20% of the total intraseasonal rainfall variation in Lubis and Jacobi 2015. And Kelvin wave also increased the probability of extreme rain event over land region by up to 60% of the baseline probability in Lubis and Rospati 2020 and Ferrat et al. 2020. And also, Kelvin wave contribute of the magnitude of the wind reversal that associated with quasi-biennial oscillation or QBO. And that's make Kelvin wave are one of the most important wave to be studied, especially the characteristic of Kelvin wave in its season and layers. And for the better analysis, we use Global Positioning System Radio Occultation or GPSRO in the upper troposphere and lower stratosphere or UTLS layers. GPSRO is accurate data for analyzing atmospheric profile, and GPS data has the highest accuracy in the upper troposphere and lower stratosphere. And then the advantage of GPSRO data are global coverage, long-term data stability, and high vertical resolution. And the purpose of this research is for analyzing the characteristic of Kelvin wave in the upper troposphere and lower stratosphere using GPSRO data. And the next is methodology of our research. We use study area from along the equator and in altitude 10 to 30 km. And then for analysis of wave spectrum, we use 3 height. There is 10, 18, and 30 km to represent each layer. 10 km is to represent the upper of troposphere. And then in the 18 km is to represent tropopause, and then the last is in the 30 km is to represent lower stratosphere. And then I use dry temperature data from GPSRO measurement for 13 years. And the data is from January 2002 until December 2014. And also I use NCR Common Language or NCL for data processing. And then in the beginning, in the first step, I did an anomaly to eliminate the seasonal cycle and climatological. And then I did the trending procedure to remove the trend from GPSRO data. And the next I did the SDSA or space-time spectral analysis procedure to see the dispersion relation of the observed wave. And then the last I did filtering wave number and frequency for Kelvin wave. And then the next is result of our research. In the first result is about relational dispersion analysis of the Kelvin wave. In the figure 2, shown diagram of space-time spectral analysis, and in the left graph or in the left picture, show wave spectrum in altitude 10 km. In these layers, the wave have low frequency and long period. And then the next graph in the middle, in 18 km, revealed that wave spectrum more steep than in the 10 km. And then the frequency in this layer is bigger than 10 km, and then have short period when compared to wave in the 10 km. And the last graph in the right side, in 30 km, show that wave spectrum more steep than 10 or 18 km wave spectrum. And these layers also have short period and high frequency. And based on these 3 graphs, reveal that in the 10 km, Kelvin wave spectrum affected by convective activity, and that's make propagation of the Kelvin wave slower in atmosphere. And the next is space-time spectral analysis in every season. In the picture on the left side is SDSA on DGF, and the next is SDSA in MEM, and then GGA and SON. And then the altitude 10 to 30 kilometers sorted from top to the bottom. In this analysis, we feel that Kelvin wave getting stronger with increasing the altitude. This is indicated by steep of the wave spectrum and passage speed of the wave. And also, if you look in more in 18 and 30 kilometer, the wave is stronger than 10 kilometer. And also in season JJ and SON, the wave is stronger too than DGF and MLM season. And the next result is analysis of the particle structure of temperature and atmospheric stability. In figure 4, show every season into longitude was selected before in the 105 degree east and 135 degree east, and this longitude is represented in Indonesian area. In this foregraph in the left side is for longitude 105 degree east, and foregraph in the right side is for longitude in 135 degree east. If we look in more in every season, the height of tropopause that marked by red line in the middle in every graph show that the height has changing between 100 meter to 1 kilometer. And in seasonal, in dry season, which is in JJA and SON, the height of tropopause is lower than wet season or in the DGF and MIM season. And the next result is Kelvin wave vertical propagation and analysis. And in this analysis, reveal that Kelvin wave propagate to eastward based on height and propagate downward for the time. In figure 5 on the left side, show longitude height section in 31 May 2002 and 24 July 2007. And this figure revealed that the fluctuation were dominant at 17 until 27 kilometer, with the largest amplitude is around the tropopause. In figure 5, show that Kelvin wave propagate eastward for the height. And then in the figure 6, show that time height section in longitude 105 degree east and 135 degree east. This figure revealed that in JJA in 1 June until 31 July, Kelvin wave more clearly detected and getting stronger in this layer. And also in figure 6 show that Kelvin wave propagate downward over the time. And then the next one is figure 7, show that Kelvin wave activity in altitude 18 km in every longitude. And this figure show that Kelvin wave is propagate to eastward. And the last analysis is analysis of ground phase, solar frequency, equivalent depth, passage speed, and vertical wavelength. I do analysis to get vertical wave number in every layer. And the first step, I calculate the potential temperature, and then I calculate ground phase solar frequency. And then I can get vertical wave number to get vertical wavelength of Kelvin wave. And then to get passage speed of Kelvin wave, I get equation from Houghton 2004. And the next is table 2, which contain about characteristic Kelvin wave in every season and layers. In 10 km or in the upper troposphere, there is no difference in the characteristic of each season. This is also occur at in the altitude of 30 km or in the lower stratosphere. And in the 10 and 30 km, the vertical propagation is downward propagation with time and eastward facilitated with height. And periodicity 1 to 17 days with zonal wave number 1 to 4. And passage speed in 10 km is between 8.9 until 15.7 meter per second, while in the 30 km is 15.7 until 38.3 meter per second. And then the equivalent depth in the 10 km is 8 until 25 meter with 2.8 until 4.9 kilometer. While in the 30 km, equivalent depth is 25 until 130 meter with 1.9 until 12.1 kilometer. The differences characteristic occur in the 18 kilometer. In the JF season, Kelvin wave more lower than MEM, DJA, and SON. This can be identified by from equivalent depth. In the JF, that is in between 8 until 25 meter, and another season is 8 until 50 meter. And also, passage speed in the JF season is between 8.9 until 15.7 meter per second, with vertical wavelength 2.8 until 4.9 kilometer. In another season, there is in MEM, JJA, and SON, high passage speed between 8.9 until 22.1 meter per second, with vertical wave number between 2.8 until 7 kilometer. And then the last is conclusion of our research is analysis of temperature fluctuation using GPS arrow data show Kelvin wave characteristic with its word propagation for altitude, downward propagation with time. And then the dominant Kelvin wave observed in temperature fluctuation in the altitude range between 15 until 30 kilometers. And then the Kelvin wave period in all years range from 4 to 17 days with number 1 to 4, and then vertical wave number range from 2.8 until 4.9 kilometer in the upper troposphere, and then between 2.8 until 7 kilometer in the tropopause, and then 4.9 until 12.1 kilometer in the lower stratosphere. And then the Kelvin wave activity in the lower stratosphere and tropopause layer strengthened in the JJA and SON season, while in the upper troposphere, and the Kelvin wave has a lower phase speed because it's coupled with convection process. And then the last is Kelvin wave characteristic in the upper troposphere and lower stratosphere are not affected by the season. I think that's all my presentation. Thank you.